we're very happy to welcome as our next speaker, Olivier Ezratty from EPITA Quantum Energy Initiative. So please take it away.
Which is cool because I won't talk about either AI or error correction, maybe a little bit of error correction and the overhead, but my talk is about energetics of quantum computing. I'm here as a co-founder of an initiative that was born 3 years ago called the Quantum Energy Initiative. It's a mix of academics and industry vendors who are looking at the energetic cost of whatever quantum technology there is, but mostly focused on quantum computing. And what we try to do in this initiative is to first, create a new discipline, because it's a very transversal discipline across multiple domains, hardware, software, economics, and so-called SDG, so looking at the environmental impact of new technologies. And what we want to do, basically, is to avoid what we have right now in AI, so creating huge systems which cost a lot, and make sure that we design as early on as possible, mixing academic and industry work, systems which care about the energetic impact before they are being deployed and not after, like we had with LLMs recently. So it requires creating a new way to look at these problems in a very transversal way, not just look at each of the pieces together. So it requires a kind of integration way to look at those systems. So when you look at the definition of what's a quantum advantage with computing, usually you start with speed. So it's about getting faster. That was the initial promise a while ago. If you come back to Richard Feynman and Manin and Benioff, we know that the benefits from quantum computing can be different. It can be also to have better results. So we know that in chemical simulations, you may not have a speed up, but maybe a better result. Same for heuristics to improve combinatorial optimization. Then you have also potentially, typically in machine learning, even though it's a very controversial topic, the capability to reduce the size of training data set. In some cases, it may happen because you have better way to explore your Hilbert space within your computer. And the last one is the energetic advantage, which has been promoted by some vendors as a potential additional benefit of quantum computer. And I define two ways of crafting this advantage. Either you are in a situation, which is the first one on the top left, where you do something with a quantum computer that you can potentially do with a classical computer, and then you can make a comparison. And in that case, you are better with the quantum solution compared to the classical solution. So this is an advantage where you compare actual things. The second situation, and you will see why I use that word, which is the acceptability, is when you do something with an FTQC system that's not possible on a classical system. So there's no possible comparison. You can't compare, or you compare with something that's infinite, I would say. And then you get some energy and power consumption, and you have to ask the question, is it acceptable? And why should it be acceptable? Because in some situation, the power and energy may be very low and it's okay. But in other situations, you will see that's the case for some vendors, you are probably above the acceptability threshold. So you have to ask the question, is it worthwhile? So the last one, which is very easy to understand, it must be usable. It must be, there must be some utility. The usefulness is important, but that's not the topic of discussion. There was a panel earlier this day on use cases in various verticals. When I try to talk about energetics, I try to approach the topic in multiple dimensions. I'm an engineer. I love physics. I love mathematics. I love engineering. But one of the key aspects is the economics. Economics is very important. And I think we lack economic understanding of what's going to be brought by quantum systems. So if you take a quantum computer, you talk about practical benefits. So it's faster, all that I said before. But then the economical benefit is the result of that. So an economical benefit is increased revenue, reduced costs, whatever. It's something you can measure economically. Then you have to look at the cost. The cost structure of a system is a mix of CapEx and OpEx. I don't know if you know these names, but capital expenses, so that's why you acquire, and OpEx, operating expenses, is the ongoing cost. And so you have two options. Either you buy a system if you are in the defense industry or a government or a cloud vendor. So you acquire a system that's CapEx, and then the OpEx is people, infrastructure, cooling, and energy. And if you look at the history of HPC, most of the OpEx is energy. And it was true in classical systems. It's probably going to be true for computers, even though the product life cycle and the materials being used to create the product may have some impact, but the balance between materials and energy may be different with computing, quantum computing. And what the first study that has been done, for example, by Alice and Bob, show that the energetic cost may be way above the material cost of the system. So OpEx and CapEx. But if you are an end user who doesn't acquire a system, everything is going to be an OpEx. So the OpEx is going to be the cost you pay to your cloud vendor, and the cloud vendor will have you pay for the energy in the end. So because it's somebody else who is charged with that. And then you have a weird acronym that comes from the IT world that nobody knows in the quantum world. It's called an ROI, return on investment. So ROI is a division between the cost, called the total cost of ownership, and the business value. And it must be below 1, but way below 1. And what you got to know as a vendor is that cost should be below 7%. Why is that? Because 7% is usually the maximum share of the IT expenses within company compared to their revenue. And so usually you compute the ROI that must be below that percentage, usually. So that's very important for analysts. And in the end, there is another phenomenon where energetics will play a role as well, which is that the versatility and the platform effect of those systems will play a role in the so-called externalities. Because if you have a volume market, if you can have economies of scale in the electronics, in everything you put in the system, you will reduce the cost of the system. And then you will reduce the cost of the energy and everything else. So it's very important to think about it. So for example, right now we have a very fragmented market, 80 to 19 different players, various technologies. It's very fragmented, and it won't generate those economies of scale, particularly with the people who say, oh, we're going to have a different algorithm for different hardware. It won't work. We need economies of scale, so we need to be sure that we have standards at the software level to make sure that we drive these economies of scale. So just to set the stage. Okay, so now let's look at the existing energy consumption in the world, in IT. This is based on 3 years old data. I don't have any more recent data, but it's very comprehensive. If you look at the energy cost worldwide, it's basically 40% is on servers and 60% is on devices. TVs, your watch, smartphones, PCs. And if you look at the server side, what you see is half of the energy is consumed by telecom companies. So moving the bits costs as well as processing the bits, which is counterintuitive. Nobody knows that. And then if you look at the share of HPC, so scientific computing and HPC, it's only 0.5% of the total energetic cost. But if you look at the cloud, so including Amazon, Google, all the servers from companies who are somewhere on the cloud, whatever the modality, it's about 20-25%. And the big question I have, and it's a question I don't have the answer, is quantum computing gonna be a share or increasing the share of HPC? Or is it gonna be a share of the bigger slice, which is regular operations in the cloud? And the answer lies with algorithms. The answer is about, will we do only chemical simulation with quantum computers? In that case, it's going to be a share of HPC. Or will we run operations, business operations, which include optimizations, machine learning, financial portfolio optimization? And in that case, quantum computer will take a share of that bigger slice. And this is a question which connects hardware and software. It's a very important one. So how do you measure energy consumption of a quantum computer? There are 3 buckets of sources of consumption. The first one, which is very known, it's electronics. And electronics contains a lot of things. So here there's 3 columns. You see atom and ions, photons in the middle, and then every solid state circuit you can have, like superconducting qubits, silicon qubits, even NV centers potentially. And electronics is about controlling the qubit. So the qubit itself doesn't consume a lot of energy because it's quantum objects, very small, picowatts of energy. It's very small. But the main source of energy is in the electronics. And if you control atoms, it's mostly lasers. Typically with cold atoms, you have a lot of lasers, between 6 and 7 lasers, depending on the technology. And you need a lot of lasers to control the atoms. And so that costs a lot. And what people don't know, usually they talk about cryogenics. Cryogenics is below, so it's the cooling. You need to cool all the systems. The only difference is some systems need to be cooled at about 15 millikelvin, so superconducting qubits. Silicon qubits, it's about half a Kelvin to 1 Kelvin. And then all the others, cold atoms, ions, and photons, they usually need some cooling at between 3 and 4K for whatever reason. Particularly the photons, they need to cool the source and the detectors. There's no way out of that. On computing, you may avoid that for communication, but not on computing for single photon handling. And then on top of that, something that is very important, it's classical computing. Because a quantum computer contains classical systems. And for 3 reasons. One is error correction and driving the system, because the electronics is driven by classical systems. Then you have on top of error correction, you have compiling, and there's some issues to deal with there. And then you have the classical computing that prepares your code. And in some situations, it costs a lot, which I will show later. One example here is, let's say you want to do some chemical simulation. One of the most famous algorithms is QPE, quantum phase estimate. So this quantum phase estimate is a quantum circuit that I show here. It's based on modular exponentiation, then some QFT that you can sometimes avoid. And it's similar to what you do with Shor algorithm. But then what you need to do is you need to prepare the simulation. This preparation costs a lot because first you need to create a state vector that fits the system, and the state vector must have a small overlap with the target state vector. And it costs a lot to compute that because the closer you are, the cheaper is going to be your simulation. So you need to do a lot there. But you need also to prepare the unitaries that are exponentiated in the circuit itself. So you have 2 significant costs. And there's a lot of details in this slide. You can browse that slowly, but the O's are different. What's costly is the top one, state vector encoding. Preparing the unitaries is less costly. There are many approximation methods which helps you do that. And then you have to post-process what you've done. So you get the results, you post-process it, and you get your ground state estimate, for example. That's what you search. So it's just an example, but it shows that the cost of classical computing around the quantum computing is important and must be accounted for when you look at the energetic of your system. So you need to have a holistic view of everything that's in the system. Compilation is about the same. Compilation is going to be costly because right now the compilers don't cost much because they compile very small circuits with a couple thousand gates. But in the future, when you will have millions of physical qubits and thousands of logical qubits, the cost is going to be important. And I don't have time to explain what's in my complicated slide, but the difference is important to understand. The main difference is, compared to classical systems, the code contains the data. So what it means is every time you change the data, you recompile your code, which is not true for your email or whatever software you use on your PC or your Mac or your smartphone. So it means that compiling is going to be a recurring cost. So if you compile a large circuit on a repetitive basis, you have to look at the cost. Both the computing cost, the time it takes, and the energy it consumes. Otherwise, you lose a source of energy consumption. So it's a new problem that is not addressed right now. The reason is we don't compile large circuits right now. That changes the landscape. So you've seen the cost. Another cost is coming from the overhead of error correction. So you've probably heard about the Willow chip that was announced and publicized last year in December and earlier in August. So what we know, and there's a lot of numbers in my slides over there, but what we'll see is a bit later. I always provide the source of the data. So what you know is if you want to support 1 million operations on the superconducting qubits from Google, you will need about 1,400 physical qubits just to get that level, 1 megaquark, like John Preskill is saying. And with that, it's just 1 logical qubit for just memory error correction that Google did. Then you need to correct 1 logical qubit, a gate, 2 qubit gate, the magic state distillation, all that stuff. And the plan of Google, which is very aggressive, is to squeeze 10K physical qubit on the chip, which is very aggressive, 10 by 10 centimeter. I don't know how they're going to do that, but let's say they do that. You need more than 7 qubits to do some stuff. You need at least 100 logical qubits. So what does it mean? In the case of Google, and it's going to be the case for anybody, you will need to assemble multiple processors and connect them together. And this is my next slide, which is in my book, for those who know my book. Whatever the technology, you will need interconnect technology. Because There are some technologies where you scale up to a large number of physical qubits, others not. It depends on the plans, on the technology that's being used, cold atoms, trapped ions, whatever. And in most of the cases, you will need to use at least one or two of interconnect technologies. One is microwave interconnect for the superconducting qubits. And in many cases, you will need to add photonic interconnect, which will require memory that is being done by friends from Willing who are there. And so you will need that. And so if you want to account for the energy consumption, you need to account also for that. You need to account for circuit partitioning, which is going to distribute your quantum circuit across multiple QPUs. And this is going to add a cost, maybe some overhead compared to having everything on a single processor. So this has to be accounted for, and nobody has done the computation on that. So, and you need to do that for 2,000 logical qubits. So that has to be done. So another thing which is very important is if you look at the resource estimates for interesting algorithms, typically in chemical simulation or physics simulation, you have two kinds of estimates that have been done by DARPA in the QBI program and by those guys from JQI, an analyst company based across multiple countries, many in the US. They did compile about 200 case studies from the future with a lot of physical qubits and logical qubits. And what they discovered is two things. If you want to simulate the ground state of a chemical compound, it's very costly. It's very costly in time. That's what you see on the yellow zone here. So it's more than 1 month of computing time based on different qubit modalities. So some qubits are faster than others. So we know that cold atoms and trapped ions are a bit slow, so they're more on the right. Solid state qubits are faster, they're more on the left, but still it's very long computing time. But there is another category called quantum dynamics, which is cheaper in computing time, but it still needs a lot of physical qubits. So in some situations, you will have prohibitive computing time, even with thousands of logical qubits. So it's going to be a new problem to fix. And to fix that problem, you need to address the constraints of multiple variables. One is the total energy of your computing, and the other one is the time. And when you divide the energy by the time, you get the power on the plug. So the power is different from the energy. The energy is the total cost. The power is how much cost you drain by hour. So how do you optimize that system? You will optimize that system with either having a shorter circuit and optimized code. You can optimize the time of your execution with faster gates, for example, or faster error correction. And you can optimize the power with diminishing the time with low power consumption systems. And so if you want to parallelize your circuit and you want to save time, you need to run in parallel the same circuit across multiple QPUs. But it has to be done if it's affordable. And you will see that it's not necessarily easy with all the systems. So you see the balance? Time and power are kind of opposite figures of merit in that case. I call it the EFP framework. I'm still working on it with the team from the QAI, but it's a framework to design the system and look at those three parameters. And so now let's look at the power consumption of the existing HPC. So the 0.4% of the total. It's spread across about 400 systems, which are accounted for in the top 500, on the top 500, only 200 have documented power estimates. And if you take the total HPCs in the world, there are only 93 of them which have a power drain of more than 1 megawatt, only 9 who are above 10 megawatt, and the top one is at 38 megawatt. And half of that is in US mostly. The total power consumption of HPCs in US is 200 megawatt. Got it? Now, what's going to be the power estimates for quantum computers based on estimates from the vendors, A, B, C, D, H in my list, the green ones, and compared to the gray ones, which are the largest HPCs in the world. So you may wonder why I don't name them in the slides. The reason is it may change. The second reason is you may not know, you may not be sure. Technology can make some improvement, but I can still name them. So on the left, you've got PsiQuantum and Xanadu, photonic systems. On the right, you have cold atoms, silicon qubits, and trapped ions. And in the middle, mostly superconducting qubits. And you see we can make two observations over there. One is that on some modalities, you are either on the right or on the left. And other modalities that superconducting qubits, with the difference between IBM, Alexandre and North Quantic, different overhead for error correction. Photonic qubits, because PsiQuantum and Xanadu are on the left, but Candela potentially are in the middle or on the right. So it means that even within a given modality, you have different technology options which will have an impact on the power consumption. But what I don't know yet is there a correlation or an anti-correlation between the cost and the feasibility, the technology feasibility of the technology? The best would be the smaller the cost, the easier it would be to realize. But when you look at PsiQuantum and Xanadu, they cost, even with one machine, the same as all the FPCs in the US. I'm not sure it's acceptable, so they will have to improve their systems. Otherwise, it's not going to be acceptable, and you won't drive a volume market. So you're back on the economics. No volume, no market, not that interesting. So we need to be on the right. So we need to design systems that are on the right, particularly when you need to parallelize their system. And the reason why you need to parallelize is the time is too long. And by the way, ions and cold atoms, which are on the right, they are slow. So we need to have a low cost for the system to be able to parallelize it. See? So you see that the energetics is a mix of economics, science, technology development, integration. And that's why I love it, because I'm an engineer. So we have to address those issues very quickly. Thank you for your attention. And as usual, you get the slides with the QR code right away on your phone.
Thanks a lot for the really fascinating talk. We have some time for questions, so please raise your hand if you'd like to ask a question.
Yeah, cool. Somebody over there?
Yep,
yeah.
I'll just bring you the microphone. No, you have to use the microphone.
No, you have, because it's recorded, I think. So.
It's recorded. I'm in much pressure. So I do want to. So first, first, thank you for the talk. It's very impressive, and I do want to make a comment on the classical side, which is related to the AI energy consumption, and apparently it's becoming a big concern right now. So I mean, AI, GPU, data center energy consumption is like on the level of gigawatts. Yeah.
Yep.
So I first of all, myself is working on how to implement AI on quantum computers, and I'm interested in knowing to what level of, say, QPU excursion of such AI models would you estimate to be beneficial in terms of energy?
For AI, you mean?
Yeah.
Well, I don't. I will respond with beliefs. My belief is I don't think quantum computing is going to help us reduce the consumption of LLMs with the gigawatt factories. There are two reasons for that. One is we don't yet have any algorithm that could run an LLM on quantum computer. Yeah. That's going to be interesting. The second is I don't believe, it's a belief, my response is a belief. I don't believe that quantum computers are going to use in real time for end user systems. It's going to be used for back-end stuff. So for example, as far as we know with AI and quantum, it may be useful to do some training for the system, but probably not for inferences.
Well, so as a researcher in this field, I would make some comments on this. So the actual research that has been done is for inference, not for training.
Sorry?
The actual research that has been done is for inference, not for training.
For quantum AI, you mean?
Yes, quantum LLM, running GPT on quantum computers, is the existing, say, speed up that has been shown is for inference, not for training. Yeah, just let you know.
I could argue about that because it depends on the models, and I've seen papers being published on improving, let's say, reinforcement learning at the training level.
Yeah.
But I have not seen anything credible with running LLM inferences on the quantum system, and we could discuss.
Apparently, we can't do that, but we can do
data,
theoretical analysis on the speed up, for example. Yeah, but speed up is speed up, but we also want to show that quantum computers consumes much less energy because AI.
But there's no proof. Right now, there's no proof.
We aim to do that, but it's apparently an astronomical amount of details to work on, which is a gigantic project. So I guess that's...
Okay, another one here.
Sorry for the time.
And there?
Yeah, okay, we'll have these two questions and then we'll have to move on.
Yeah, he's next. So
Plenty of questions. That's good. Really, on that slide, Olivier, you have 4,000 logical qubits. That's your base.
yeah, it's kind of threshold with a number of gates. It's not just the qubits.
Yeah, okay.
Yeah.
My point is the relationship between logical and physical one depends on the
Yep.
correction methodology used, depends on the technology.
Yeah, connectivity between the qubits as well.
Yeah, but that's maybe the technology. How is it how is it going to evolve? Because some technology we know they are kind of behind others, and maybe evolutions of this connectivity and this will influence this ratio and maybe the graph.
Of course,
And
it's
then
going to
how-
evolve over time. Yeah.
Exactly. Is this reinforcing what you are showing us, or reinforcing the trend of what you are showing us, or is it the opposite?
What you can expect based on the roadmaps of all the vendors is going to make progress getting on the right. I hope so. But for example, when I asked the question to the folks from PsiQuantum, they told me that, and IBM as well, what they told me is they would reach that threshold even at 100 logical qubit. But their plans were to have economies of scale which would keep them at the same level of energy and power consumption and improve the number of logical qubits. So it's already built in my visual over there. It's built in. So they expect some progress. I can give you an example. The typical example is electronics on 100 logical qubit can be based on using FPGAs, and they plan to switch from FPGAs to ASIC, which should help them reduce the power consumption and improve the speed as well. So it's built in my model over there, yeah. Same for Colladome, same for ions and everywhere. The last one?
Hello. In the beginning, towards the beginning, so you've shown a graph that had like, I think 0.4% as a target energy consumption for...
target, existing.
Could you get there?
Yeah, it's the beginning. It's not target, it's existing. It's
Yes.
classical power consumption of legacy systems. Yeah.
So, I mean, as you know, technologies start to consume less energy per operation or like become less costly in some way, their usage increases.
Jevons effect.
I think
Rebound effect or Jevons effect.
So how do you think quantum computing is going to positively impact the energy share of the HPC market, if that's within the realm of possibilities?
So what's your question? How is it going to increase? Oh, we have no idea. We don't know. We don't know. Either you are in a replacement scenario where the quantum computer replaces a small or big share of existing HPC. What we can expect based on what we know about the use cases, it's going to add some energy consumption on top of existing system, because we know that in most of the cases we won't replace existing HPC. It's just be an addition. So what will be good? It's it's going to be a small addition of the big one. And what we can expect also is if we are in a scenario where quantum computers are just being used for research, applied research, develop new molecules or whatever in that small share, it's not going to be a big share, I would say. What we can expect is if and when quantum computers are being used for optimization and regular business operations, it may be a big slice of the 20% slice that we have here. But the thing is that share depends on getting the right algorithms, which we don't have yet. So there's a lot of uncertainty. Now, so uncertainty mixed to uncertainty, another one, and you don't know if we're going to have 4,000 logical qubits someday. So, but it's worthwhile to ask the question right now. And by the way, another way to answer that is to say that if you look at the energetics and the power consumption of a system, it forces you to have a holistic view of the whole system. So it's good for the optimization, for even other figures of merit of the system. That's why it's useful to think about it right now. But there are many uncertainties.
I think we're going to have to.
I think he's going to cut.
We're going to have to move
he's
on.
the next speaker, so he wants to speak.
But you can find Olivier afterwards for more chats.
I'm going to be at the cocktail party at the Rue d'Hauteville, so you can ping me, whatever.
Let's thank Olivier again for a really nice, fascinating talk.